All right. Good afternoon, everyone. Welcome to the next lecture, lecture number 5. Today we're going to talk about radiation, electromagnetic radiation, and antennas. So, yeah, everything that we're going to talk about today is all based on Maxwell equations, right? I don't want to um, waste my time on the on this slide that I used to show before. Let us just maybe say that using these Maxwell equations, we derive the wave equations. In the case of no currents and no charges, right? So we prove that electromagnetic fields can exist in space, in nature, even without without charges, in form of electromagnetic wave radiation. All right, so today we're gonna talk in a little bit more detail on how this radiation um, happens, right? Yeah, so and the starting point is to ask what is an antenna and why we need an antenna. Right, so last time we discussed this waveguiding modes, waveguides, and transmission lines, like shown here. These two pieces of wire, closely spaced pieces of wire. We say that this structure supports waveguiding modes, and the characteristic of this waveguiding mode is the fact that the currents or current elements in these two wires, they oscillate in opposite phase. Okay, for example, if in one time instant the current points to the right in the upper wire, it points to the left in the lower wire, and it changes like from point to point, but always the current is polarized in in opposite phase. That oscillates with opposite phase. Uh, Only such a mode can be propagating along this system without radiation, because any current, if it oscillates, it radiates, and in order to cancel down this radiation, the second wire must be polarized in the opposite phase. So for this case, we have no radiation. But what if we need to couple the energy or outcouple the energy from this transmission line, right? Let us consider this edge or ending elements here. And let's say in one time instant, in the upper wire, the current points to the left, and in the lower wire, it points to the right, or I mean, whatever. So this system does not radiate. But if I bend these two ends of the transmission line, the current that used to point to the right, now it points upward, and this second current points upward too. So upon this transformation of modification of the transmission line, I get a line segment that drives the current in the same direction. So now these two elements point in the same direction and oscillate in the same the same phase. And such a system now already can radiate. So these two pieces of wire can play a role of an antenna. Not only radiation, antenna can be used to transform freely propagating field to the transmission line waveguiding modes, okay, like demonstrated here. And depending on this operation mode, we call the first type the transmitting mode, transmitting antenna, and the second type is receiving mode or receiving receiving antenna. So the definition of an antenna is a device that is designed to effectively transmit or receive electromagnetic waves by converting waveguiding modes into freely propagating waves and vice versa, freely propagating to waveguiding modes. All right, so let us talk about the radiation, why the radiation happens, and then we will discuss the antennas in more details. But before before talking about radiation, let's talk about the point like charge, okay, and what happens or what can happen if a charge starts to move, okay. So let me consider a stationary charge like an electron, right? We know that this charge in a rest frame, right? So now this charge is stationary, it doesn't move. We know the electric field for such a charge, right? It's a Coulomb's law, which is proportional, the field, the electric field is proportional to the charge value and inversely proportional to the distance squared. So the further from the charge, the lower the field. I can consider the same charge, but from another frame, from the moving frame. Okay, so it's a charge that I used to describe in the rest frame, and now I'm considered the same charge with creating the same field, but from the moving frame. Okay, you know this principle of relativity that says that all laws of physics are the same in all inertial frames, right? Like you can ask, for example, am I moving right now or not, right? In my frame, I'm not moving right now, but at the same time, we are all at the surface of the Earth, and the Earth moves through the space around the sun with a large velocity. So depending on the frame, I am in the rest or I'm in the move. That really depends on the consideration frame. So I can consider the same charge from the moving frame, okay? And the calculations show that if this velocity of this moving frame is not large, is much smaller than the speed of light, okay, we come to these formulas for the electric and magnetic field. So electric field is more or less the same, but the magnetic field appears, right? So for the rest charge, it was 0. For the moving charge, or considering the same charge from the moving frame, we get magnetic field, which is proportional to the electric field of this charge. So we come to the conclusion that magnetic field is a relativistic effect. Okay, so magnetic field can be regarded as a relativistic effect that appears because of the presence of electric field. So in this example, we considered what kind of effects we can observe just considering a charge in different frames, rest frame versus moving frame, without acceleration, right? So it's a inertial frame. So now let us consider the same charge, but subject to acceleration. Okay, so again, starting from the resting charge, it creates the electric field of this symmetric distribution electric field. Now I make this charge like abruptly accelerate, like impulse acceleration. Okay, so accelerated and then stop. So what happens, right? Because the information that this charge got acceleration propagates with the finite velocity, the areas distant from this charge, this unperturbed area, keeps the same field of the resting charge. Okay, so this area doesn't know that the charge was moved. At the same time, inside of this sphere, perturbed field, right? It is a field that has been changed because of this abrupt acceleration. And this area, this sphere, kind of propagates outward from the charge in the form of radiation. To describe this process, we introduce the retardation time, right? So it's a time before which the field is not aware of the change, and after this retardation time, the field changes. And this retardation time is finite because the speed of light is finite. The field in the entire space cannot change abruptly or quickly. It takes time for this information about this acceleration to propagate from the charge. So based on this fact and using Maxwell equations, we can derive the formulas for the electric and magnetic field in the entire space around this accelerated charge. To do so, I'm gonna skip the details, just give you a hint how to do so. So we're starting from electric and magnetic field and use the scalar and vectoral potentials, phi and A. We discussed them when we talk about the static electric and magnetic field. Right, we use the solutions for the potentials. of the scalar potential and vector potential. The vector potential depends on the velocity of the charge, but at the retardation time, which is important because if you substitute these potentials to the field definitions, we get these expressions here. And when we take the curl of the vector potential, we need to take the curl of the velocity, but at the retarded time, okay, which depends on r. So this curl of velocity is not just special derivative of the velocity, it also includes the time derivation. Okay, so this is important. This important point to notice this fact. And so after these calculations that I skip, we come to these equations for electric and magnetic field around the charge. So here we recognize the first term, which is inversely proportional to the r squared, right? So which is exactly the static field. So it's a static field of the after this acceleration. Okay, this is the first term. In the electric field and magnetic field also gets the form of Biot-Savart Laplace equation, which is magnetic field of moving charge. Okay, so it's a static part or static like part, because these things depend on time or can depend on time, but their form, mathematical form, is exactly like static field. However, we also get the second term in these two equations, which is inversely proportional to the r to the power 1, right? So it's inversely proportional to the r. This function 1 over r decays much slower than 1 over r squared. 1 over r squared depends much faster as I go away from the charge. So these two terms, called static near field or static like near field, and radiation far field. Radiation far field because this radiation part propagates or decays much slower than this near field. All right. So also from these equations, we conclude that electric field and magnetic field of this radiated field are orthogonal. Okay, they are mutually orthogonal, and they also are orthogonal to the direction, to the point of interest. This r hat is the unit vector in the point of interest. So electric field and magnetic field are orthogonal in the far field, and they both are orthogonal to the propagation direction. And then probably the main conclusion from this slide is the fact that radiation as the effect occurs just because of the retardation. Okay, so without retardation, we wouldn't have radiation. This is very important point to recognize. Any radiation happens because of the retardation, simply because of the fact that the speed of light is finite. Yeah. So this is about accelerated charge. But what if my
Doctor,
charge? Yes,
Dr.
yeah,
Farr, I have a
totally.
question. So is the static like field the same thing as like a near field or the Fresnel zone that you would use in antennas? Like the
Yeah,
near
we will.
field that you would use in antennas?
Yeah, we will come to that fact, to that point.
Okay,
Yes,
okay, sorry.
yeah, it's related to that. This
Okay,
near
you can
field, yeah,
continue.
it's
Okay.
uh yeah. So now I'm making my charge not just abruptly accelerate, but oscillate in time harmonically. Okay, so the coordinate changes as the cosine function omega t, where omega is the angular frequency, right? So for this coordinate, I can take the derivative and find the velocity, which is the sinusoidal function, and taking derivative of the sinusoidal function, I get the acceleration, right? So substituting this acceleration function to these equations for the electric and magnetic field, I come to these equations for the electric and magnetic field, the radiated electric and magnetic field. Important point to notice here is that electric and magnetic field in the radiated electric and magnetic field, they oscillate with the same phase. Okay. Um, Electric and magnetic field oscillate with the same phase. And now I'm interested in how this electric and magnetic field distributed in space. To do so, I introduce the spherical coordinate system, right, with theta counting from the z direction, and I oscillate my charge along the z direction. Right, phi is the angle counted from the x, and r hat is points outward in the direction of the propagation, and theta and phi hat are unit vectors on the surface of the sphere. Right. So I can write for the for the radiated electric and magnetic field equations in these components. So electric field depend on theta, and the magnetic field depends on theta and point in orthogonal to the electric field, and also explicitly indicate that use the fact that the time is retarded by the value r over c. Right. So in order to describe how this radiation or radiated power is distributed in space, we introduce the value to quantity of Poynting vector. Okay, so Poynting vector is an important quantity, which is simply the cross product of radiated electric and magnetic field. Not only radiated, but for now we are considering the radiated part of the field. So we take radiated magnetic radiated field, right? And if you substitute these two equations in this definition of Poynting vector, we will get the product of these functions and the cross product of the unit vectors theta and phi, which is simply r. Okay, so we conclude that the Poynting vector, which describes the direction of the radiated field, is radially oriented, right? It's oriented along the radius from this on this sphere. Uh, yeah, and this is the value of this Poynting vector. So these functions depend on time, and I can take I can compute the average over the period of this oscillation of my pointing vector, and this is the result. This function depends on the direction theta as a sine squared, okay, which is the function, I mean, which has the shape of this donut-like shape. Okay, so it doesn't change in this xy plane, but changes as a like shape as a donut or 8 or butterfly, right? It's called, sometimes it's called relay butterfly. So this cross section of this donut. So this is the radiation pattern, the simplest radiation pattern of an oscillating charge. So this radiation pattern describes the radiated power or radiated power density depending on the direction in space. And from this pattern, we see that this charge radiates mostly orthogonal to the direction of its oscillation and doesn't radiate in this direction. So no radiation along z direction. Do you have any questions, by the way? Okay. So now let us bring another charge to the discussion. So let's say here we consider it a positive charge. Now we bring another one, negative charge, and put them on a small distance. Okay. So such a system is called a dipole. And the electric field lines of this system, of this dipole, is presented on this this picture. So from these vector lines, we immediately see that between or around, in a closed proximity to this dipole, the system gets more electric field lines. Okay, so it means, comparing to the Sol charge, which basically means the fact that if I come closer and closer to the system, the electric field grows faster than the electric field of a single charge. Okay, so if, for example, in a single charge we have this Coulomb's law with r squared in the denominator, right? For a dipole, we get 1 over r cubed. And taking into account that when I come to this system, r gets smaller, so this factor grows. So electric field around the dipole grows faster than the electric field around the charge. Okay. Yeah, so this is the formula describing the electric field distribution around a dipole with a dipole moment P. So dipole moment is simply the charge over one of these charges, right? Charge quantity multiplied by the distance between positive and negative charge. So it's a dipole moment. Okay, so this function describes the dependence of the electric field lines around the dipole. So now if I do the same procedure and derive the electric field after this acceleration or oscillation of the dipole, okay, so I can, for example, assume that my dipole, the distance between positive and negative charge like changes as a harmonic function, right? So using the same procedure, I come to this to this formula for the electric field around the dipole. So again, here we recognize this static-like near field, which coincides with this static field, right, up to this exponential harmonic function. And the second term, which again depends on the distance as 1 over r. So you see this difference. The near field decays as 1 over r cubed, so much faster decays as I go away from my dipole, and where only this radiation part survives. Okay. At the same time, this radiation far field part completely coincide with the radiation from a charge. Okay, so it simply means that from if I consider my system far away from the system, I don't see a difference between the charge and the dipole, so their radiation is the same. The only difference is this dipole moment. Okay, the dipole moment of the system. So since this is the same function, it also depends on this sine of theta. Similarly, finding the Poynting vector, calculating the Poynting vector function, we can plot this radiation pattern, which is again this Rayleigh butterfly sine squared function. And if I integrate this radiation over entire spherical surface, I get the total radiated power from this dipole. Two key points here to recognize is first that the fact that radiated power depends on the dipole moment quadratically. Okay, so square p dipole moment square. The larger if dipole moment is twice larger, the radiated power is 4 times larger, right? And this dependence on the frequency. The higher frequency, the higher radiated power, and this power is 4. All right. So from these two examples, we notice that the radiation power from a single charge or from this oscillating dipole, the radiated field is the same. However, the near field can depend on distance as a 1 over cubed, or r to the power of 3, or 1 over r to the power of 2. And for more complicated systems, okay, so I can consider a system of dipoles, or like a more complicated system consisting of many elements, the general rule is keeps same. The far field is more or less, I mean, it all depends as a function of distance 1 over r. It can get different dependence on the angle. The fact that we're gonna discuss today, this radiation pattern can be different. But the near field is always different, right? So near field is a more complicated function. But we can discuss the main kind of characteristics of near field and far field. Okay, so let's say for the near field, we can introduce the distance at which the near field decays enough so we can consider only the far field. Okay, so typically it happens at the distance more than a wavelength of radiation. So wavelengths, wavelengths is the distance that wave propagates per period of one oscillation. So at the distance smaller than the wavelengths, we have a strong contribution of the near field, but at the distance of larger than wavelengths or several wavelengths, the field is mostly far field. Okay, so this is the first point. Second point is that far field can freely propagate and move the energy away from the radiator, from the antenna. However, the near field doesn't propagate. Okay, so if you look at the near field of an antenna, you will see that the pointing vector of this near field starts at antenna and then goes back to the antenna. So this picture distribution of this near field is much more much more complicated, but it starts and returns back to the antenna. So it's not non-radiating field. Okay, so it's non-radiating field. And why they are not radiating? This is simply because of the fact that for a field to be radiating, electric and magnetic field have to oscillate in phase. Okay, only oscillation in phase makes the field radiating. The near field, in the near field, the phase between electric and magnetic field changes with the distance from antenna, but they have significant phase difference between electric and magnetic field. So and this phase difference make this fields non-radiating. Let us consider different types of antennas. So first of all, how to make it? Yeah, so first of all, we distinguish antennas by the operation mode. So in the transmitting mode, we drive our antenna, the current on the antenna, and by using some sort of generator, right? And this current oscillates in time, just like our dipole oscillating in time. And this oscillation of current creates the radiated field, as demonstrated here for the radiated field shown in green. In the receiving mode, inversely, right, or reciprocally, we can use the same antenna, but illuminated by external incoming field. This E field now is incoming field, and as you can see, this incoming field can drive the current in the back and forth in this antenna, and this current can be absorbed by some sort of a load shown here by this R connected to this antenna. Okay, so transmitting and receiving mode. A linear antenna, meaning no active elements. Any linear antenna can work in both transmitting and receiving mode with the same efficiency. Okay, according to the so-called reciprocity theorem. However, active antennas can work differently in transmitting and receiving mode. So another classification of antennas by their operation principle. Okay, so the simplest antenna, like shown here, is the dipole, because it gets two wires that are sufficiently short. Okay, such an antenna, like realistic dipole antenna, is shown here. So it gets two metallic wires, two metallic parts, and this is the waveguide that allows some wave come to this antenna and drive the current along these dipole parts. Another type is monopole antenna. So monopole antenna, I mean, according to the name, right? Mono means one, so it's a one shoulder, one part. So it's a one single wire antenna. However, this monopole antenna usually connects to the ground or to the box, to the body of the device, right? Like if you have a transmitter that uses this antenna, so this second element, this box, the body of this device, plays the role of the second element. Sometimes, especially at radio frequencies, you know that the ground, for example, is the well-conducting medium. Okay, the ground, and you can ground a monopole antenna, and your ground will play a role of the second element, effectively reducing the size of the antenna by half. All right, another type of antenna, which is like more directive antenna, called Yagi-Uda or Yagi antenna. Okay, so in this case, we have an active dipole element in here or here, and then a number of directors, which are passive elements, and one or several reflectors. Okay, so these passive elements, they are designed to kind of guide the radiated field from this active element to this direction, to the right, and I mean through constructive interference, and block the radiation to the left because of the destructive interference. Okay, so and designing these passive elements, directors and reflectors, we can achieve a very high directivity. So basically, such an antenna can be very, very directive. Another example is a parabolic or dish antenna, right? So that works more or less like a metallic mirror in optics. So basically forms a focus in some of this focal point, and yeah, and this antenna also achieves a very high directivity, much higher than the typical Yugi antenna. Helical antennas allow to radiate waves with particular helicity or circular polarization. Okay, like this one, this antenna allows to radiate waves with clockwise polarization, which is sometimes useful for communications. Okay, so these waves with particular defined circular polarization more robust, for example, to the noise. And of course, microstrip or patch antennas. These antennas are in all of cell phones, like smartphones. All of these small smartphones equipped with different kind of patch antennas. And finally, we can distinguish antennas by the operation frequency. Okay, so RF antenna, because RF is corresponds to the longest wavelengths. Okay, longest wavelengths. The antenna itself is the largest. So, and typically in RF, our antennas are quite large. Like shown here, this monopole antenna is very bulky. If you reduce the operation wavelengths to the microwave frequency range, we use microwave antennas. So here the wavelength is few centimeters, like from 1 to, let's say, 10 centimeters, or better say from few millimeters to several centimeters. Anyway, so the characteristic size of antenna is always more or less comparable with the operation wavelengths. So in this case, the antenna becomes smaller, right? And typical example of a microwave antenna is the patch antenna used in our cell phones. If we reduce the wavelengths even more, we enter the millimeter or terahertz frequency range, and in this frequency range, we also have antennas. They have different geometry, different design. So here I'm showing this patch terahertz antenna. And the characteristic size here is several hundreds of micrometers. Okay. And if I go even further, I am entering the optical frequency range where the characteristic size of the antenna becomes smaller than comparable or smaller than 1 micrometer. Okay, so in this case, this device fabricated at Creole, which is the University of Central Florida device that includes these dipole antennas, and the size of this dipole antenna is comparable to 1 micrometer. And this device works in the infrared frequency range. And even if I make these elements even smaller, right, I can make these antennas working even in the visible or even in the at the shorter wavelengths. Okay, so like shown here, this is the optical version of the Yagi-Uda antenna. Again, so this central element is the active, so it radiates, and then this number of passive elements, they re-scatter the radiated field to form the narrow radiation pattern because of the destructive and constructive interference. And the rest of today's lecture, I'm gonna spend discussing the characteristics of antennas, like the main characteristics of antennas. So, and the very first and maybe the most important one is the characteristic that describes the ability of antenna to convert localized or waveguiding modes to free propagating modes, right? Because this is the main purpose of any antenna, to make this transition from localized modes or waveguiding modes to freely propagating modes. So again, let us consider this transmission line that is connected to this dipole antenna here. This system radiates electromagnetic wave, and effectively we can describe this radiation or the presence of this antenna. We can describe it by introducing some sort of a load that represents the action of this antenna. I denoted by Z in. So this in means input. So it's an input impedance of antenna. Input impedance of antenna. So this input impedance of antenna, in general, can be complex, right? So this real part, represented by these two terms, are R small and RL, which represent the radiation resistance and loss. Okay, so these two represent the loss of energy in some form. This loss can be because of the dissipation of energy in my antenna, just conversion into heat, right? And radiation, which is the main purpose of the antenna, to radiate electromagnetic field. So this radiation leads to the fact that the energy in my system dissipates in the form of radiation, right? And I can describe this process using this R sub R, radiation resistance. The second part, which is imaginary, this imaginary part is a reactance. This reactance accounts for the stored energy in the near field of my antenna. Okay, so when I drive the current in my antenna, a part of this energy is radiated, and I take into account is using this radiation resistance. But the other part of this energy can be stored in a reactive power around this antenna without radiation. Okay, so and this reactance describes this reactive power. So introducing this input impedance, now I can describe the antenna in terms of lumped element parameters, right? And represent my antenna as a load connected to the transmission line. In this case, I can use this standard approach for calculation of the scattering coefficient, gamma. We derived this formula 2 weeks ago, right? Which depends on the input impedance of this load of this antenna and Z sub 0, which is the characteristic impedance of the transmission line. Okay, which is usually it's a real value. For coaxial cable, it is standard 50 ohm. Okay, so this Z0 is typically it's 50 ohm. In order to describe what part of the power actually gets to the antenna, right? So I'm sending the signal through in form of the propagating mode through this transmission line. This transmission line comes to the antenna, and in general case, a part of this radiation reflects back. Okay, and so this is some sort of a loss. I'm losing this energy in form of reflection. The purpose of my antenna is to reduce or eliminate this reflection completely. So I'm introducing this delivered power, which depends on the reflection coefficient, right? So if reflection, delivered, let me see, reflection coefficient describe the part that is reflected when it's 1, then yes, then delivered power is 0. So the only case when the delivered power is equal to the incident power when the reflection coefficient is 0, when it's vanishing, right? And that can happen when the input impedance of my antenna is equal to the transmission line characteristic impedance. So more rigorous analysis shows that this actually happens when the input impedance of antenna is complex conjugated to the transmission line characteristic impedance. But typically, transmission line characteristic impedance is real valued. So these two guys simply must be equal. Which means that so if transmission line characteristic impedance is real valued, right? That means that in order to achieve this phase matching regime, the input in the imaginary part, this reactance, must be 0 for the antenna, and the real part, which is radiation loss and dissipation loss, must be equal to the transmission line characteristic impedance, right? So this picture demonstrates a typical dependence of a resistance and reactance. So resistance is these two guys, R radiation plus R loss. this blue curve. And reactance is this guy, this X input impedance. So this reactance that accounts for the stored energy in the near field of my antenna. So you see that these two terms, they strongly depend on frequency, right? And I immediately notice 2 points here and here where the reactance is vanishing. Okay, so here and here, the stored radiation, stored reactive power of my antenna is 0, vanishes. So my antenna here and here converts the energy into propagating field. However, in order to get rid of the reflectance, I also need to make these two guys equal to the characteristic impedance of the transmission line, right? So let's say if my transmission line or coaxial cable gets 50 ohms, then the operation regime somewhere here, where reactance is 0 and resistance is small, all right, like maybe a few tenths, will be matched. Okay, so the antenna will be most effective in the area around here. In contrast to this regime here, when yes, reactance is 0, but the resistance is much larger than the characteristic impedance of my antenna. Oh, sorry, characteristic impedance of the transmission line. So here antenna reflects a lot back to the transmission line. Here antenna almost doesn't reflect back to the transmission line and works as a good radiator. All right. Do you have any questions regarding this part? All right. Radiation efficiency. So this is very simple. Only part of delivered energy to the antenna is radiated in form of radiation, right? The other part, of course, is converted to the dissipation loss. And radiation efficiency is just the quantity that describes which part of the delivered energy is converted to the radiation. Okay, and, it is equal to the ratio of radiated resistance to the sum of radiation plus loss. Yeah, so you can consider this radiation efficiency as a quality, not a quality factor, but the quality of the antenna. Because when this radiation efficiency is small, let's say 10%, that means that antenna is radiates only, or better say, consumes only 10% from the total consumed energy in form of radiation, and the other 90% of consumed energy is consumed in form of dissipation. So that antenna is not that good. Okay. Another important characteristic of antenna is antenna radiation pattern and directivity. Okay. So antenna not only converts localized or waveguiding modes to free propagating radiation, it also can form a desired radiation pattern. Sometimes we need omnidirectional antennas. omnidirectional antenna means that an antenna that radiates in all directions similarly. Okay, like the radiation pattern, which we define as the electric field squared multiplied by r squared. So you remember that in the far field, in the radiation field zone, the electric field is inversely proportional to the distance, to the r. So the square is proportional to 1 over r squared, and multiplying by r squared simply means that I get rid of the dependence on the distance, and the function is defined that this way is proportional to the radiated power or radiated power density to the specific direction denoted by theta and phi, right? And doesn't depend on the distance. A typical radiation pattern looks like this. So it gets several lobes. One main lobe is the direction of main radiation, right? Some number of side lobes that point to the direction, but the direction of interest, and also this back lobe that radiates backward. For example, a Yagi-Uda antenna gets the radiation pattern that looks like this. So sometimes we need omnidirectional antenna that radiates symmetrically in all directions. Like for example, for communications, right? For communication, like cell phone communication, we need antennas that can receive information from any direction symmetrically, okay, isotropically. However, for other applications like TV or satellite communication or something like that, we need to form a narrow main lobe, okay, because this forming of narrow radiation pattern allow us to concentrate more and more energy into a specific direction and achieve a higher or better communication because of this narrow radiation pattern. All right. So in order to numerically describe the the ability of antenna to form directed beam lobe, we introduce the function of maximum directivity. Okay, so maximum directivity describes the density, the radiation density in the direction of the main lobe, this maximum radiation direction. So for example, here it's a 0 angle divided by the total radiated power. Okay, so we take into account the fraction of the total radiation to all possible directions to the total radiated power, and we multiply this function by 4 pi to normalize the directivity. So the directivity of unidirectional source, unidirectional antenna, which is antenna that radiates isotropically in all directions, right? So in that case, the directivity, maximum directivity is 1, is unit. So we normalize this to the isotropic radiation. yeah, I didn't put the numbers here. So typical numbers for the direction for the maximum directivity. 1 for isotropic, 1.5 for small dipole, something like 1.6, 1.7 for 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 a longer dipole antenna, something like from 10 to 100 for Yagi-Uda antenna, and this value can reach thousands for high large aperture antennas like this dish uh, type antenna. So this value, this directivity can change in uh, large dimensions, right? From units up to thousands and probably millions. So in order to describe this characteristic, we introduce this directivity in dBi scale, right? So I here stands for isotropic, meaning that we normalize this value to the zero for isotropic isotropic radiation. Yeah, and in order to achieve like a systems with very high radiation directivity, we can use this approach of phased array antennas. Okay, so we simply use the fact that if radiation from different antennas is coherent, then the total radiation from the entire system is the superposition of all these partial radiations from every of these antennas. And if I put many of these radiators, many of these antennas, using this approach, I can achieve like very high radiation directivity. And on top of that, if I change the phase of radiation from these antennas, I can also manipulate with this main lobe. So I can achieve the beam steering effect. I can control this direction of the main lobe. And finally, a few words about oh, I didn't change the title of this slide. A few words about the bandwidths. Okay, it's because when we use antennas for communication, we always modulate our wave using frequency modulation, amplitude modulation, mixture of them, and so on. So it's sort of any sort of modulation leads to the finite bandwidths of my signal. Okay, so typically the transmission signal bandwidth looks like this. So it's centered around some frequency, and then it expands from this frequency by a factor, by some value, and at the level of 3 dB, this is what we call the bandwidth of the signal. Okay, and the bandwidth of my antenna, which is simply the difference between the highest frequency and the lowest frequency at the level of also the level of 3 dB. This bandwidth must be equal or larger than the bandwidth of my signal, right? Only in this case, my antenna will transmit and receive the data without distortions. Okay, so for communication, for data, I need antenna with large enough bandwidth. At the same time, the bandwidth is closely connected to antenna quality factor. Okay, so by definition, quality factor is the ratio of the stored energy to the radiated energy. The larger the stored energy, the larger quality factor. So this is a little bit misleading concept because quality, like usually quality, the higher quality, the better, right? Like larger quality factor usually means a better system. Like the larger quality factor of a resonator means that our resonator is better. It keeps the energy, stores the energy for a longer time, However, in the antenna community, we also use this quality factor, but here the higher quality factor, the worse, because higher quality factor means larger stored energy in the system, and this is not what we want from the antenna. We need this energy to be radiated, not stored. Still, this quality factor is inversely proportional to the bandwidth, and the formula that connects the antenna bandwidth and the quality factor is this one. So the bandwidth is inversely proportional to the quality factor. We need for a given antenna, especially for data, for communications, we need the quality factor as low as possible. At the same time, antennas can be quite bulky, right? And antenna is typically the largest element in the communication system. And quite often, from the practical point of view, we want to make antenna as small as possible. Okay, even in our cell phones, this patch antenna acquires quite a lot of space inside of our cell phone, and we need to make this antenna as small as possible. However, it's not possible because there is a fundamental limit. It's called Chu limit that connects the size of the typical size of the antenna, this A, okay, and the minimal possible quality factor of the antenna. Again, the lower quality factor, the better for antenna. The lower quality factor, the better. So this Chu limit simply tells us that if I make my antenna smaller and smaller, I'm reducing this A, right? This ratio will get higher and higher. So smaller antenna makes the minimum quality factor larger and larger. Okay, so if I'm limited by a particular bandwidth of my communication channel, I cannot go below some particular size for my antenna, right? Like for our cell phone, which operates at the frequency around something around 3 gigahertz, this characteristic size is like maybe centimeter or so. So it's we cannot make antenna smaller than this limit. Do you have any questions about this part? All right. So this is basically the end of my today's lecture. Next week is for the lab 5, and we will be simulating like an antenna and antenna characteristics. Okay, so I will make this assignment shortly this week. And so thank you very much. This is the end. Let me stop my recording and then we can discuss if you have any questions.